Assalamu alaikum dear students, we're back with another video lesson. In the previous lesson we were talking about standing waves. We said that standing waves, it is a wave pattern that of course it occurs or it happens, it generates when we have two waves of the same frequency, wavelength and amplitude. They're moving in the same medium but in opposite direction. And then after that we said for standing waves we have nodes and antinodes, and we've learned about different different standing waves and how we can find the length of every standing wave. And the equation for that was 2 times the length divided by the number of antinodes there. And of course, we've learned how to calculate the wavelength and all that. We said the wavelength between, or the length between two adjacent nodes or two adjacent antinodes, that is equal to half of a wavelength, Basha, and the distance between three adjacent we can also say that the distance between three adjacent nodes or antinodes, that is equal to one full wavelength. We also said that the distance between the adjacent an antinode and an adjacent node, that is equal to 1/4 of a wavelength. We solved a lot of questions and then we left some other. All right, so let's just dive into solving the remaining of the questions, or the questions that are left. All right, so we left at question number 4, and I need you to mark this question well because this is important. It says the stretched, also questions like this been in Nozari many times. But let's say a stretched string fixed at both ends, which is 2 meters long. What are 3 wavelengths, Basha? You can underline this. This is the length, right? What are 3 wavelengths that will produce a standing wave on this string, Basha? So we want 3 wavelengths that produce standing wave here, and then name at least 1 wavelength that would not produce a standing wave and explain your answer. Zohar Basha. So let's talk about this one for a second. Now, I need you to watch this one here. If you remember, good man, this is a standing wave, right? This would be the next standing wave that we can have. Let's change this color. This is the next standing wave, right? And of course, you can do even more. These are all standing waves. Let's get my equation, the equation that we have. The question says, name 3 wavelengths that will produce standing wave. One wavelength, 2 times the length, right, divided by what? Divided by the number of antinodes. Basha? Now, you can also write this as a node as well, right? Any antinode that is a whole number, all right, would allow the wavelength to be a standing wave. In other words here, how many antinodes do I have in the first standing wave? That is 1, right? And yeah, 1 antinode. What about here? 2. What about here? 3. So as long as the number of antinode is a whole number, right? As long as the number of antinode is a whole number, then that wave, all right, will produce a standing wave. Or that wavelength, let's say, that wavelength will produce what? Will produce a standing wave. Standing wave, Basha. What if the antinode is not a whole number? If any number, as long as it is not a whole number. What do I mean by not a whole number? For example, like 0.5, 1.2, 3.5, 3.9. As long as it is not a whole number, right? If the antinode is not a whole number, then it will not produce a standing wave. It will not produce a standing wave. Produce a standing wave. All right. Zohar Basha. So let's test this theory here. Now, got my 3 wavelengths that produce a standing wave. Basha, the first wavelength we can say. One wavelength 2 times the length divided by the number of antinodes. Basha, in the first standing wave, how many antinodes we have? 2. So the length that is given, by the way, is 2. And yeah. Okay, it's 2. We're just double checking, right? It is 2. All right. So that'll be 2 times 2. The first standing wave that I can have is just 1, right? So the first wavelength that can produce a standing wave, it is a wavelength that is 4 meters long. By the way, can I write 100 instead of 1? Absolutely fine, as long as you write a whole number. Basha? So this is the first wavelength here. Now another wavelength, second one, that produces standing wave. We can say 2 times 2 divided by 2 again. So it is going to be 2 meters. Basha? The third wavelength, that produces standing wave, as long as these are whole number. 2 times 2 divided by 3, right? It is going to be what? It is going to be 4 divided by 3, that is 1.3. Watch. I need you to watch this carefully. Bob, it's totally fine for the wavelength to be a digit here, or to be a decimal number. That's perfectly fine. As long as the whole number is, as long as the number of antinode is a whole number. So as long as the antinode is a whole number, whatever the wavelength you get, it is perfectly fine. Each one of these wavelengths will produce a standing wave. Totally fine. So these are 3 wavelengths that produce a standing wave. Now give me one wavelength that will not produce a standing wave. Basha, you can do the same thing. 2 times the length, which is 2, divided by the number of antinode. Baba Gutman, for the wavelength not to be a standing wave, Basha, or not to produce a standing wave, the antinode that gets beaten, Jmarachi, Bablin, what is it called in Kurdish, right? Jmarachi. Seriously. All right, so it should not be a whole number. Basha? All right, so like what, for example? Like it could be 0.5. It could be 0.7. It could be 2.4. It could be any number, as long as it is not a whole number. Basha? So now let's just say 1.5. Basha? So now it is going to be 4 divided by 1.5. What is it equal to now? Is it 3? Whoa, what are you saying? It's 2 points. All right, so 4, honestly, I feel like, use a calculator, Baba. So 4 divided by 1.5, it is going to be 2.67. All right, that is by rounding here. So this wavelength here, it is not going to produce a standing wave. Don't forget. And I hope you heard me right. Okay, so these are the wavelengths that will produce a standing wave as long as there is the number of antinodes. And we have a question similar to this actually. All right, what is the other question that we have? One of the chapter review questions. They'll give us a bunch of wavelength. Basha says we have different wavelength. Let's say we have 3 meter, right? We have, let's say, okay, let's just write this one here. Okay, let's say we have 3 meter, Basha, and then we have 6 meter, and then we have 7 meter, and then we can have, let's say, 10 meter too. The question would say, all right, we have a string. The string is, let's say, 3 meter long, Basha. Which one of these waves will produce a standing wave on this or that string there? Okay, so what do you do now? You're going to do exactly the same, but reverse. What do we mean by this? I'm going to go wavelength the 2 times the length of the string divided by the number of antinode. But later, wavelength is already given. When Baba will make the antinode the subject here. 2 times the length divided by the wavelength here. Once you do the division, agar antinode ka jmare to now I will remember. Agar jmare to in that case, that will produce a standing wave. But if the antinode is not a whole number, then that wave will not produce a standing wave. So let's just check it out. The first one here that we're going to get, for example, is going to be 2 times 3, all right, divided by what? Divided, the length of, the length of the string is 3. So 2 times 3, okay, 2 times 3, divide by the number, wait a second. So that is, the length is 3, the wavelength is also 3. So this to cancel out, it is going to be 2 antinode. If it is a whole number, it will produce a standing wave. So the first one, yes. What about the second one? Right? Let's say 2 times 3 divided by 6, right? Yeah? So again, 6 over 6, that is also, that will be 1. So that is also, the second wave is also producing a standing wave. What about the third one here? Basha, again, 2 times the length, which is 3, divided by 7 here. That is going to be 6 over 7. And then that, of course, equal to 0 point something, right? 0 point something, because it is not a whole number, 0 point something, this wave, it is not going to produce a standing wave. What about the last one here? Okay, that is 2 times 3 divided by 10. That is again going to be 6 over 10. That is 0.61, yeah. So this one is also not going to produce a standing wave. So in this case, it is just going to be this A and B here. It is likely, for example, if 2 options are correct, option D is going to be, for example, both A and B, for example, one, yeah. If not, it is just one option that is correct. But al-muhim now, you got the idea. So you could do this one. All right, so that is the answer to that question. Now, let me tell you a little regarding this diagram right here. Okay. Now, but once again, if you want to understand this one, I believe I'll have to show you this one more time, just so that, you know what we just studied here. So once we go here, right, watch this. Later, if you notice here, this wave can go from side to side one, yeah? Okay. And you can see here, that is what I need you to know at this point. Then now we can go back to our diagram here, because this is the diagram from a book, by the way. It's never been in Wizari. I'll just tell you this just in case, Yani. So what do we have at this point? I'll just tell you the key regarding this one there. Okay, maybe we don't have to go to the whiteboard. We'll just do it here, so that you can see what do we have. Let's not hide this one. And that is what we have. Where's the eraser? Good. Watch this. Here's a standing wave that we have. Need to pay close attention to this. Okay? So this is one of the standing wave that we have. Actually, you can start this one here according to this one. And then this is, you do know that this is a node. This is a node, so there's no motion on nodes here, and there's a node. And these, of course, this is an antinode. Okay, now watch this. We know that in one full cycle, the particle, it is going to move up, and then move back to the equilibrium, then go to the other side, and then go back to the same point. That'll be one full cycle. Do you agree with me, right? That is one full wavelength. Basha, what if we start from the top of a wave here? Does it matter? No. So starting from the top of a wave, perhaps maybe I'll need to remind you the pendulum too here. So we said if we have a pendulum here, okay, what is one full period? Starting from this point here, right, all the way to the other end, right, let's call this one A. It has to go to the equilibrium point and then back, go to all the way to the other end B here. That is going to be half a period. And then back to point A, that'll be one full period. That is one full period, yeah? So it's the same thing that we have. If we have a wave starting at this point here, the time it takes to go all the way to the other end, that'll be half a period, yeah? And then back to the same point, that'll be one full period. So now what we have is, if we're going to, now we don't need this any longer, I guess. Starting from this position here, right? Right, this position here. If we start the time here, we can say the period at this point is 0 here. Now, if we consider one particle right here, right? This particle, it is going to move all the way to the other side in here, right? But man, for this particle, right, to go all the way to the other end, how much time will it take in here? But man, that'll be half a period, right? So for this particle, but if this particle go to there, so what do you think will be the shape of the shape of the wave here? This is how it is going to be, right? So this particle would be going here, and this particle would go all the way there. But the point is, for particle, let's just call this one here. For this particle to go from this point, point A, all the way to point, let's call this one to point C, Basha. We said it would be what? It would take half a period here. So we can see that the time here, right, it is going to be half a period. Or you could just say delta T, the time it took, it is just going to be half of the period here. Basha? Now, once again, in order to make one full cycle, then this point or particle has to vibrate all the way back to the same point. That would be one full cycle. Basha, bear with me. But man, from point A to point C, it is going to be half a period one, yeah? Basha, what about from point A to the equilibrium here? It is not to C yet. It just, for example, this particle is moving from point A to point B here. دواد let's see to point C, that would be half a period. Kata, what about from point A to point B? Basha قال لي half beat, and what would be the period here? Can I say it is going to be 1/4 of the period? Or you can say 2/8 of a period. Makes no difference, yes or no? You can always simplify, right? But the point is, let's just keep that in mind. All right, so the period here from point A to point B, don't forget, all right? From point A to point B, the time it takes, it is going to be what? If this is half a period, this is going to be 1/4 of the period. Basha? So how would the wave look like? In this case, of course, the wave is going to be straight. Basha? And then, Basha, what if I take another point back, let's say? So what if I say, what if the wave is at this point here? Basha? Let's not draw this one here. Perhaps maybe I'll have to get rid of these so that things are much clearer here. Basha? And this one too. Okay. And let's just erase these as well. In order for this particle, don't forget to go from A all the way to the bottom. That would take half a period. So if we go back in here, for this particle, watch this, for this particle to go only to this point here, but if at this point here, if it is half a period, later the beta 1/4 of the period. Basha, what if it is coming to this point right here? Bika section, for example, if this is 1/4, what do you think this period would be here? Can I say it is going to be, that is in this case is going to be 1/8? Yes. Every time, for example, like you want to, or if you're doing this, whatever the time you have to divide by 2 or cut that in half. So later, if this point or this particle comes to this point here, it is going to be half a period here. Basha, if it is at this point, it is going to be 1/4 of a period. See, half of that is going to be 1/4. What if it is right at this point here? It is going to be 1/8, we can say, Basha, of a period, or you can say of a total period. Now, I need you to, let me just, hopefully understood this. Now, let me explain this one here a little. So this is what we have. This is the wave that we have, Basha. All right, now this wave, it is moving all the way to the other end. So this point, it is going to flip all the way to the other end. But does it happen instantly? No, it is slowly going to do that one, This is the equilibrium position. So from point A to go all the way to the other side, the time it takes is going to be half of the total period. Basha? And if it goes back all the way to point A, that'll be 1 full period, but we don't want that. Basha, if at this point, if from point A all the way to point B, it is half a period, what about from point A to the equilibrium position? Perhaps maybe it would be best if I bring back the pendulum. That might also, of course, help us here. I'm hoping that most of you understand this, but only for those who have no idea still, I'll just explain a little bit further, and I hope it's worth it. Yeah. If you have a pendulum, that is the equilibrium position, right? Starting from this point all the way to the other end, let's call this one A. Call this one A, and call this one B. Basha? So the time it takes from point A all the way to point B, right? The time it takes, it is going to be half of a period. If it goes back all the way to point A, that'll be 1 full period. Goes back to point A, that is the time it takes, it is equal to 1 full period. But we don't need this here. Basha? What about if I say, now we know that the time it takes from A to point B here, that would be half a period, yes? What if I just want this time here? The time it takes from point A, let's call this point C here, from point A to point C. Isn't that half of this time that we have? Yes. Basha, get over 1/2b at the edit end. It is 1/4 of a period. So the time would be 1/4 of a period. What exactly is this one here? My data point A, Baba. From point A all the way to the equilibrium position, that is 1/4 of a period. Basha, and this is exactly what we have. All right, Basha, what if I don't want this? I need the time, for example, from point A to this point right here, which is this point. It is right in between point A and point C. Basha, قليلة 1 over 4b. What do you think this point is? Can I call this one 1 over 8? Yes, right? 1 over what? 1 over 8 of a period here. So the time it takes to get to this point, all right, that'll be 1 over 8 of a period. If it continues, that'll be half 1 over 4 of a period. If it continues to point B, that is going to be half a period. Then if it goes back, of course, then goes back to the same point, that'll be 1 full period. Basha, later got man 1 over 8 one, yeah? Later 1 over 4. What about at this point here? One, yeah? This point here. What will be the answer to that? Of course, you can see that it is going to be 3 over 8 of a period. Basha, later 1 over 8. Later the beta 2 over 8, which is 1 over 4. Here is going to be 3 over 8. All right, and then here it's going to be what? 4 over 8, which is going to be 1 over 2. It's the same thing as if you, for example, divide this one into, let's say, 8 pieces, all right? So that'll be 1 over 8, right? That'll be 2 over 8, which is 1 over 4, 3 over 8, and then 4 over 8. Then you can simplify the numbers, and then they would take the same time to go back, all right? So the point is, Baba, just remember the keywords. The most thing that this ever be in Wizari, they will say, for example, all right, they say for a point, they might give you this diagram. So let's get rid of this one. They might give you this diagram, Basha. They'll say a point at A, Basha, it is moving, and they might give you this diagram too here. For a point from A to go all the way to the other side here, how long does it take? It has taken half of a total period. What about from a point from A to go all the way, let's say, to the equilibrium? You can always draw the pendulum diagram. It helps you the most at this point. Then you can make the correct or the right judgment here. Then you can tell what happens here. And that is what we have. I just wanted to tell you this, even though it took a lot of time, but hopefully it's worth it. And this is the other part of what we said earlier. Give one wavelength that does not or will not produce a standing wave. That'll be it. Zor Basha. Shtachidi Kashman hey Baba. Rahan sends a series of pulses of amplitude 24 centimeter down a string that is attached to a post at one end. Basha. It is attached to a post at one end. Assuming that the pulses are reflected with no loss of amplitude, what is the amplitude at a point on the string where the two pulses cross if the string is rigidly attached? Remember the keyword? If it is rigidly attached, the pulses are sent, right? Once reflected, they are inverted too. When you got if there's no loss in the amplitude, these two, of course, would cancel each other out. So the resultant amplitude is going to be 0 centimeter. That is the first part of the question. The second part says, the end of which, Basha, or at which the reflection occurs is free to slide up and down. If it is free, all right, in this case, these pulses are, the pulses that are sent, right, these are reflected but not inverted. So now these two, once they meet, it's going to be constructive. If the amplitude is 24, so 24, we add them, 24 and 24 is going to be 48 centimeter right here. This is a very important question. It's been in Wizari so many times, so I need you to be aware of them. And I've already mentioned or gave you an example regarding how to solve this one, and I hope you'll remember. That was the next, if you'll remember, earlier, okay, of this video, you could say. Which of the following wavelengths produce standing waves on a string that is 3.5 meter long? Basha, so we have the length of the string here, okay? We have the length of the string, which is, okay. We have the length of the string. Length of command send the Baba, it is 3.5 meter long. That is the length of a string. So now we have a bunch of wavelengths here. By the way, this is not a multiple choice, all right? It could be more than one, it could be one, it doesn't matter. So these are no multiple choice. Which one of these wavelengths is going to produce a standing wave on this string here? We said we have an equation, wavelength that's 2 times the length divided by what? Divided by the number of antinodes. Well, yeah? Because we're given, all right, the length and the wavelength here, we're going to find the number of antinodes. And if once you find the number of antinodes, if it is a whole number, Basha, then that wave will produce a standing wave. If it is not a whole number, then it will not produce the standing wave. So let's try the first one here. 2 times the length, which is 3.5 meter, right, divided by 1.75 meter. Okay, so now 2 times 3.5, it is going to be 7, right? So 7 divided by 1.75. 1.75, the answer is going to be 4. So you can see that 4 antinodes, it is a whole number. So the first wave, it is producing a standing wave. What about the next one here? All right, the second one, 3.5, right? So 2 times the length, which is 3.5, divided by 3.5. These two cancel out, so it is equal to 2 meter. So that is also, 2 antinodes in here. So that is also going to, because the antinode is a whole number, so this one is also producing a standing wave. What about the third one here? The wavelength, it is 5 meter long here. So 2 times 3.5 divided by 5, that is going to be 7 divided by 5. That is already not a whole number. So it is going to equal to 1.4. So since this is a whole number, so wave C, right, or wavelength C will not produce a standing wave. What about the last one, D, right? It is 7 meter. So 2 times 3.5 divided by 7, that is 7 over 7, which is equal to 1. So this one is also a whole number. So all of these are producing a standing wave except then C. Basha? So of course, this will be in Wuzari, and this is important. And remember this note here says you need to find the number of antinodes. Once again, if you obtain a whole number, if you get a whole number, a standing wave will form. However, if you get a fraction, no standing wave will be formed or will occur, will not be produced. Basha, and these are the solution for that. Right, now here we have 2 Wuzari questions. Let's solve this two real quick. It says Ran sends a series of pulses of amplitude 24. This is similar to the questions we've solved earlier. It says starting that, or this string, down a string that is attached to a fixed boundary. I gotta leave it. This is a keyword. Fixed boundary, all right, it is the same as a, we can see that if it is fixed boundary, the pulses will be reflected and inverted. Don't forget, Basha, at one end, assuming the pulses are reflected with no loss, same amplitude, Basha, what is the amplitude at a point when these, or on the string where 2 pulses are crossing? Then because the end is fixed here, one pulse will be going, the other pulse will be reflected and back inverted too. So these 2 will cancel out. So the resultant, or the resultant is going to be 0, Basha. And then we also have another question here. Says transverse waves shown in the figure, which of the following is correct? The wavelength, about the wavelength and the amplitude right here. Basha, this is something interesting, right? Yeah. So what you need to know is, now these are, how many wavelength do I have here? This is one wavelength from a crest to a crest. This is a normal wavelength, by the way. It's not a standing wave, so you don't have to worry. So one wavelength, that is 2 wavelength, right? So 2 wavelength, it is equal to 4. 1 wavelength dakata 2 meter. Basha. So now, which one of these wavelength dakata 2 meter? It is this. So now you can cross out B and D here. Basha. So it is either A or C. Now the amplitude is left one, yeah? We said amplitude, it is maximum displacement, either up or down, right? It cannot be from both to top. So if you divide this to, by 2, that would be just 1 here. So which one has an amplitude of 1? That is option A, because this is incorrect. So now the correct answer is A. Pretty simple. You can easily, of course, achieve these 2 marks right here. Okay, now standardized test preparation. There are some questions here. These are super important, and I always recommend you solving these. All right, what is the first question here? Or first of all, it says, base your answer to questions 1 to 5 on the information below. So we're going to use this to answer the first 5 questions here. It says what? A mass is attached to a spring, as you can see here, moves with a simple harmonic motion on a frictionless horizontal surface as shown above. Asha, the first part of the question says, in what direction does the restoring force act? Asha? Okay, so the mass is stretched, Basha, and moves with simple harmonic motion. If the mass is stretched in this case, isn't that the applied force in here? In order to stretch that, this is how you need to move. If you're stretching the mass, there is an elastic force which is always trying to bring the mass back to the equilibrium. So if you apply a force to the right, the restoring force is going to be to the left. Basha, which one is it? This mass spring system, it is not saying that it is stretched or compressed. So that, of course, makes a whole difference in here. So let's just go through the options. Is it to the left? We're not sure yet. All right. Is it to the right? We're not sure here. C says to the left or right, right, depending on whether the spring is stretched or compressed, and that'll be the correct answer here. Basha? So if the mass is stretched, Basha, that'll be to the right, so the restoring will be to the left. But if the mass is compressed, the applied force is going to be to the left. The elastic force is going to be to the right. So whether to the right or left depends on whether the spring is stretched or compressed. So this is the answer. All right, the next one that we have, still related to this question, or to this diagram here, this picture, it says, in what form is the energy in the system when the mass spring system or when the mass passes through the equilibrium position? Now, after the mass is oscillating, okay, after the mass is oscillating here, now it is back to the equilibrium, Basha. So the displacement is 0, right at this location here. Okay, so what is the energy? Let's just write this one right here. What is the energy of a system now? At maximum displacement energy, it is elastic potential energy. This elastic potential energy, it is all going to convert to kinetic energy. So at equilibrium, the energy of the system, it is kinetic energy. Basha, and how do we know in what form the energy is when the mass passes through the equilibrium? Basha, and this passes. It's not out west, so it is passing through. Is it elastic? No. Gravitational? No. Kinetic? Yes. Combination of two or more above? No. 3 says, in what form is the energy of the system when the mass is at maximum displacement? Well, if it is at maximum displacement, that is going to be this much, right? So that means the mass or the spring is stretched. If it is stretched, that is going to be elastic potential energy. Remember this is on a horizontal surface, so do not forget. So is it elastic potential energy? Yes. Is it gravitational, kinetic, or combination? It is none of these. Okay, so it is elastic, which is A here. 4 says, which of the following does not affect the period of a mass spring system? Now, before we answer this or look at the option, just write the equation of period of a mass spring system. 2 pi square root of mass over spring constant, Basha. If it is in the equation, it affects the period. If it is not in the equation, it does not affect the period. Basha, let's take a look. The mass, it says which one does not affect, so I got to leave it. So mass affects, so it is not this. Spring constant, it affects, all right? So it's not this. Amplitude of the vibration, is there amplitude in the equation? No, so amplitude does not affect the period. All of the above, that is also incorrect. Now, question 5 says, if a mass of 48 kilogram, if the mass is 48 kilogram and the spring constant is this much, what is the period of the oscillation? Now, all you have to do is just plug in the numbers into that equation, or if not, you can have it too. So, Gutman 2 pi square root of mass over k, mass of 48, and then spring constant 12. You just divide the two, you'll get 4 pi second. Right? The reason why we keep 4 pi second, Baba, because it is given there. Basha, what do you do in Wizari? How do you know which one is this? My recommendation is, you can multiply the whole thing there. If you could do that, that would be great. If not, you could just, since there's a pi in here, so multiply whatever this equal to, just times 2, so keep the pi. Basha is going to be pi times this much, or whatever the number you get in that case, that is going to be that much of a pi here, so you can do that. Baba, Garosh Nazani, you can multiply what is 4 pi equal to and write it here. What is, 8 pi equal to, write it here. What is 4 pi equal to, write it here. And pi is 340 and pi over 2, it is equal to, what is it equal to? Write the numbers here, then you could safely multiply the whole thing, whatever the number you get, that'll be that one. And that is an alternative way to do that, so you don't have to worry about how can you keep the pi. Base your answer to questions 6 to 9 on the information below. The first one that we have, so you can see that there is a pendulum. All right, it says a pendulum bob hangs from a string and moves with simple harmonic motion, as shown here. What is the restoring force in a pendulum? In a pendulum, the restoring force is what, Baba? There is a gravitational force, Fg, when you. This Fg analyzes to two components. These two angles are the same. أولى بيتا Fg cosine, يرج بيتا Fg sine theta. So now these two, this is the tension and this is Fg. These two will always cancel out. So the restoring force, it is going to be a component of gravitational force that is tangent to the pendulum's path. This is perpendicular to the path. Actually, if this is the path, this is perpendicular, but this is tangent. Yalla, let's take a look at the option. It is the total weight of the bob. No, because that is the total weight, Basha. Again, baby. It is the component of the bob's weight that is tangent to the motion of the bob. That is the correct one. Is it the component of the bob's weight that is perpendicular to the motion? No. Okay. It says the elastic force. There's no elastic force in here. Okay. All right. 7 says what? Which of the following does not affect the period of a pendulum? Once again, what is the key to answer these kind of questions? Always write the equation. If it is in the equation, it affects. If not, it does not affect. So here's the equation. Masha 2 pi radical or square root of L over gravitational acceleration here. So the first one says the length of a string. Does it? Says this question once again says does not affect. So always underline the keywords here, because if not, you might just easily lose 2 marks. Basha, does the length affect or not? It does affect, Basha. So not this one here. The mass of a pendulum, does it affect the period? No. And that is what we're looking for. All right, let's just go through the choices. The free fall acceleration, it affects the period, so we don't want this. All of the above, no. If the pendulum completes exactly 12 cycles in 2 minutes, what is the frequency of the pendulum? You have to be careful with these questions, okay? So it says it covers 12 cycles, Basha. But my frequency, the number of waves, all right, divided by what? Divided by the time. You might say, Mr. Why are you using this? If I want to find, the question says, what is the frequency, right? Since I don't have the period to find the frequency using 1 over period, as long as there is number of waves, we'll use this equation here. So number of waves divided by the time. How many waves are there? 12 cycles, means 12 vibrations, 12 oscillations in 2 minutes. But some of you might just say 2, and that is going to be 6. No, Kaka, this is minutes. Please make sure you circle or underline these. So every minute, I hope you already did not do this, right? Every minute is 60 seconds, so 2 times 60. So now 12 divided by 120, what is it equal to? It is equal to 0.1 hertz. And that is the answer to that. What if they're asking for something extra, like the period? Now the period is equal to 1 over the frequency. Basha, if the pendulum's length is this much, 2 meters long, gravitational acceleration is this much, how many complete oscillations? Oh, this is something very important, actually. This question, Benanuzari, right? Of course, perhaps with different numbers sometimes, but a lot of times students struggle to answer this question, because of this question here, you have to find the answer in 3 different steps, Basha. But there are 2 methods to do this. I'll show you both, inshallah. Yes, that's mine, Baba. Let's just bring this one. It's going to be best, actually. All right. Because we're going to need a lot of writing here, perhaps. Yalla Baba. Zor Basha, Pandola, come on here. The length is, what is the length? The length is 2 meters. Basha. Free fall acceleration. What am I? Free fall acceleration, that's it. 9.8. So you cannot use 8.1 now. That is meter per second squared. That is gravitational acceleration. The question says, how many complete oscillations does it make? Yani, number of waves, we can say, or vibrations, or oscillations, or cycles, you can say. These are all, right, same thing here. In a time that is equal to 5 minutes. Basha, now you tell me first, where do we get the number of waves in here? We get it here. So we said, we know that frequency, the number of, okay, need to go a little bit here to the side here. So we know that frequency, let's just write it here. So frequency, number of waves, or you can say cycles, Basha, divided by the time in here. Okay, so now we have the time, Basha, all right? But in order to find this one, we have the time, which is 5 minutes. It says how many cycles does it make? How many oscillations does it make in 5 minutes? So we have the time, which is 5 minutes. But in order to find the number of waves or cycles here, let's just call them oscillations. Oscillations, we need the frequency. Basha, how can I find the frequency? You're given the length and the gravitational acceleration. Basha, if you use this tool, what can you find? You can find the period. Period dakata, 2 pi radical of L over gravitational acceleration, right? So that is 2 pi multiplied by length of command sender, 2. Gravitational acceleration is 9.80. You cannot use 81, by the way. So now find the period. What is it equal to? Let's just look at this one. It is 2.84. 2.84 seconds here. Basha, once you found the period, now remember we need the frequency. Frequency decat, let's say 1 over period. So 1 over 2.484. 2.84. Basha. Now we can find the frequency. So what is the frequency equal to now? It is equal to 0.352 hertz. 0.352 hertz. Basha. Now once you found the frequency, you can easily find the number of waves or oscillations. You just have to cross multiply. Number of, let's say, oscillations or waves or whatever, it is equal to what? I don't think we have enough space there. Okay, it is equal to now frequency times the time given. But there is one thing you need to be aware of. That is 0.352 times. Remember, the time we're given it is 5 minutes. Each minute is 60 seconds. So once you multiply the two, you'll find how many oscillations does it make, which is 100. Wait a second. Okay, so it is correct. So it is going to equal to what? It is equal to 200. These numbers, these are the answer for different questions. So let me just do my calculations. It is way better. Sure, somebody says it is not correct. 0.352 times 5 times 60. Yes, the how many oscillations does it make? 105 oscillations, 0.6. Basha? 105.6. But let me ask a question here. The question says how many oscillations does it make, right? Complete oscillations, actually. Basha? So there is a key I need you to understand here. First, underline this one for me here. Okay? Yeah, come back, Kaka. Now, once the question says how many complete oscillations does it make, can I say 105.6? No, because that is not a complete, right? Can I say 106, like just round it up? No, because that is incomplete, Basha. So now we're going to do this. We'll say it is going to make 105 complete oscillations. So we're just going to remove this one here. Because we're not going to, this is not a complete, and we cannot round it up because it is not a complete number. It's not a complete oscillation. So the complete oscillations, or how many times it is going to oscillate, is going to be 105. Basha? Now, what is the other method we could have done? You found the period for one oscillation, yeah? So what is the period for one oscillation? It is 2.84 second. 2.84 second. The period, Basha, for one oscillation, 2.84 second. Basha. Now, if I have 5 minutes, which is 5 times 60 second one, yeah? This is the total time that I have. If you divide the total by the time for every oscillation, that would also give you the same number of oscillation as well, which is divided by 2.84. Once you divide the two, it gives you the same number as well. Yani, what does this look like? For example, you have $100 with you. You go to a store, and then you want to buy something, let's say, I don't know, like a dress. It could be a suit one, yeah? If the price of each one of them is 20, Basha? Okay, so you'll just divide how many suits can you buy or dress you can buy. Whatever the money you have, you just divide by the price of one suit, for example. That 100 divided by 20, in that case, you can buy 5 one, yeah? So we have the total time, and what is the time for one oscillation? Is just this much one, yeah? So total divide by 1, that gives you the same number. So let's just double check. 5 times 60, that is 300 one, yeah? 300 divided by 2.84, that is, once again, it is 100.5 or 105.6, but we said we're just going to take the complete oscillation, so it's going to be 105 oscillations. Basha, this is how many times it oscillates or makes complete oscillation. Basha, what if the question says, how many times does it pass through the equilibrium? In every oscillation, it passes through the equilibrium twice. I get it. If we have 105 oscillation, I get on the oscillation maybe. If the question says how many times does it pass through the equilibrium, in every complete oscillations, for example, this is going and then coming back, that would be one full oscillation one, yeah? So in every complete oscillation, there will be 2 times, so you could just multiply by 2. That is going to be 105 multiply by 2, whatever the answer is, that would be the correct one. What if the question says, how many amplitudes does it cover? Basha, does it cover? This is how many times it can oscillate one, yeah? In every oscillation, there would be what? There would be 4 amplitudes. So in this case, you could just multiply 105 times 4 amplitude if the question's ever asking for the amplitude. You can see it is written right here. Yeah, this is also something very important. Right? Don't underestimate these kind of easy questions, actually. It's been in Wizari so many times. Like exactly this diagram here. It says base your answer to the questions 10 to 12 on the graph below. So the first question that we have, or that would be question 10, says what kind of wave is this graph represent? All right? What kind of graph is this? Is that transverse or longitudinal? Of course, you can't say longitudinal, huh? This is a transverse, so you can see it. Okay, electromagnetic wave. Very good. How do we know this is a transverse, not an electromagnetic, Baba? As long as there's written displacement and you have crest and trough and all that, so that is a transverse wave. Basha? It says which letter on the graph is used for the wavelength? Basha? Bitman, the distance between 2 adjacent similar points, right? Crest to crest, that is wavelength, so letter C represents the wavelength. Question 12 says, which letter on the graph is used for a trough? Trough would be letter A. Don't say D because that would be for the amplitude. Zodabash. Base your answer to questions 13 and 14 to, let's say, 13 to 14 on the passage below. Bash, it's manhilira. The light wave with an amplitude of 0.75, Zodabash, has the same wavelength as the second wave with an amplitude of 0.53. The 2 waves interfere. Yeah, Basha. Question 13 says, what is the amplitude of the resultant wave if the interference is constructive? Baba, constructive, yani, add the 2 amplitudes. That would be the answer. Basha, which is 1.28. What is the amplitude of the resultant if the interference is destructive? Destructive, yani, subtract the 2 amplitudes. Obviously, big minus small one, yeah? So that is going to be 0.22 meter. Zorbash. So that is easy one, yeah? Okay, now this question is also very easy, but let's just solve them together. 2 successive crests of a transverse wave are 1.2 meter apart. Actually, this is one of the questions that is very, very important, highly recommended for Wizari too. All right, it says 2 successive crests are, so let's bring our whiteboard here. Oh, not this. Zorbash. So we have a wave. The question says 2 successive crests are. Didn't expect that. 2 successive crests are okay, 1.2 meter apart. Asha, so the distance between these two, 1.2 meter. And you do know that this is a wavelength. The wavelength is 1.2 meter. That is the wavelength. 8 crests pass a given point every 12 seconds. Now, I really need you to be careful here. Do you know that every crust that is passing through a point that is the same as saying one oscillation? Every crust represents one oscillation here. So every 12 seconds here. So we have the wavelength here. Now the next thing we need to do is find the frequency. Frequency is equal to the number of oscillations, you can say, or waves or vibrations, doesn't matter, Basha. Let's say oscillations. Oscillations, Basha, divided by what? Divided by the time. So how many crusts pass a given, let's say, point here? It says 12, one, yeah? So, 8 crusts pass. So here's 8. In what time? In 12, or every 12 seconds. So 8 divided by 12, what is it equal to? 8 divided by 12. The answer is equal to 0.67 by rounding. Basha, you can write 667, doesn't matter. 67, I hope the 7 gets better though. All right, so that is now the wavelength and the frequency. Basha, the question says what? What is the wave speed? Basha, speed the cat, frequency times wavelength. Basha, frequency 0.67 times wavelength. Come on, Sambu. But man, it is 1.2. Yalla, multiply and tell us the answer. 0.4 times 1.2. And yeah, man, the cat 0.8 meter per second. Let's say 0.8. That is going to be option B here. 0.804 specifically or precisely. Oh, we've speed the case. Now, which one of these is it? It is option B. Zorbash. What is next? What is it? Okay. Speed, calculate the frequency and period of the light wave. I believe these are easy, so no need for this. Do we have to? You're given the wavelength and you have the speed, find the frequency. Oh, what is the frequency equal to? That is for question 16. We know that speed, it is equal to, and if it is light, we can sometimes write C instead of speed, by the way. Frequency times wavelength. Frequency, that would be speed over the wavelength. You have the speed and the wavelength, just divide them, you'll find the frequency. Basha, once you find the frequency here, which is, let's say, equal to this much hertz, can you find the period? Yes, period, the cat, say 1 over the frequency. So 1 over this, then you can find the time, that is going to be second. All right, the next one. What is next? What kind of wave does not need a medium to travel through, right? Well, I think that's obvious. When you got electromagnetic waves do not need a medium to travel through. Basha. Question 8 says, list 3 wavelengths that could form a standing wave on a 2-meter string that is fixed at both ends. Basha. Whitman, this is a similar question to the ones that we've solved, was it this session or the previous session here? Says what? List 3 wavelengths that could form a standing wave on a 2-meter string here. Okay, so here's the 2-meter string, good man. Okay, so the length is 2 meters. Now the first wavelength, by the way, right, is going to be 2 times, let's write the equation, 2 times the length divided by the number of antinode. When good man, as long as there is a standing wave, the number of antinode must be a whole number. When got that the first one is 2 times 2, the length is 2, divided by the first, that is going to be 4. And another one is going to be 2 times 2 if we have 2 antinodes, and then another one we can say 2 times 2, that is divided by 3, it's going to be 1 over 1, So this is 4, this is 2, this is 1.3. Each one of these wavelengths will produce a standing wave. Basha? Okay, says a visitor to the ancient city of Erbil wishes to find the height of a lighthouse. The visitor ties a pool and all that. We've solved this question before, Now go back to the answer. It says find the length, In order to find the length, we also use the fast way too, good man. Only on Earth we can say to find the period, to find the length, by the way, good man, you can say period squared divided by 4. But this equation can only be used if the work or the experiment or whatever that is done. It is an orthogona, GK فرق بيو بلا ما كده قارة. Okay, question 20 says what? This is also one of the highly recommended questions for Wazari. I really need you to understand this one too. Okay, it says what? A harmonic wave that is traveling along a rope. Basha, the oscillator that generates the wave completes 40 vibrations in what? 40 vibrations in 30 seconds. Basha? So let's write these information. So we can say number of waves, Basha. It is 40 vibration. Isn't that the same as saying 40 oscillation? This is the same, Basha. In what time? In a time of 30 seconds. So what can we use this to find? We can use this to find the frequency. Zor Basha, that is the first part. Second says, a given crest. Basha. So let's just underline this. A given crest of the wave travel this much centimeter along the rope in a period of 10 seconds here. So here we have a wave bubbling, or a given crest, which is, you can see that. How far can it travel on a rope? It can travel 425 centimeter in a time that is equal to 10 seconds. So do not mix between these two times that is given here. So how far a point can travel in 10 seconds, so you can call this one delta x if you want to call it, because this is the distance traveled. It's not a wavelength though. The question says, what is the wavelength? And show all your work as well. Basha. But man, number of waves in time, we can use this to find the frequency. As long as there's frequency, that means you'll have to use this equation. Speed دكات, the frequency times the wavelength. One, yeah? Question says find the wavelength. How is the wavelength دكات? Say دكات, the speed over the frequency. Zohar Basha. Yeah, is that? Now, using this two, good man, we can use this two to find the frequency, right? So let's just do this one here. Let me use a different color. Basha, good man, frequency دكات. That's it. I should have used this one or wrote this one a little bit lower. How about let's just expand it. All right, yeah, look, we'll do it here. So frequency دكات, that's it. دكات, the number of waves or oscillations divided by the time. How many oscillations do we have? 40, right? That oscillations or those oscillations are made in 30 seconds. So 4 divided by 3, that is going to be 1.31, yeah? Because the two zeros cancel out. So 4 divided by 3, it is going to be 1.3331, yeah? So the frequency it is 1.333. This is in hertz, Basha. That is the frequency. Basha. So we already have found 1.333. All right. So you can take less digits than this. Now the next thing that we need the speed of the wave, Basha. But how can you find speed, Baba? This is how far a wave can travel in 10 seconds. Now speed, because we have distance and time here, so we can say speed decat, the distance over the time. But remember, there's a centimeter. If you convert that to meter, that is going to be 4.25 meter divided by 10 second one, yeah? So once you divide this, it is going to be 0.425 meter per second. That is the speed of a wave, Basha. Now, use these two numbers into the equation. So 0.425, okay, meter per second divided by the frequency, we can find the wavelength. 0.425 divided by 1.333, Basha. والله ما كذا كانت send 0.318. You could just say 0.3. You can say 0.32 meter. That is the length of a wavelength. Basha, this question is something very, very important. Why? Because you have to, or you can say this is a 3-step equation. First, you will have to find the frequency based on what is given. Second, you'll have to find the speed, right? And then eventually you can find the wavelength of the waves, or the wave here. All right? And that was the last question of this chapter, right? And by the way, if you want to master this this chapter very well, why are we here? Okay, if you want to master this chapter very well, make sure you're going to solve all these questions, because there are some questions that are very, very important. Of course, we've covered a lot of questions that has been in Wazari, but there are still a lot more. So good luck trying them. That'll be the end for this session. Till next time, which we're going to start with chapter 4, inshallah. Take care of yourself, practice well, and then Assalamu alaikum wa rahmatullah.